Good morning, one and all. I am here to introduce about Dr. Uma Mahesh NV. Dr. Uma Mahesh NV is currently Professor in Department of Civil Engineering, National Institute of Technology, Warangal. His areas of interest are water resource systems, hydrologic modeling, irrigation management, water quality modeling and management, applications of soft computing techniques, and modeling impacts of climate change. He has more than 20 journal papers and peer-reviewed articles in books. He has also published 50 national and international conferences. He has also guided 6 PhDs and now presently guiding 7 PhDs. Thank you. Now I invite Dr. Uma Mahesh NV to deliver your keynote address.
Good morning, dear friends. I'll try to speak about the extreme rainfall in urban areas. So maybe I'll just start with basic fundamentals of extreme value analysis because many of you are students. I'll just talk about extreme value analysis and how this extreme value analysis can be extended for understanding how the rainfall, extreme rainfall in urban areas is changing with climate as well as other reasons, urbanization and other reasons. And now these are some recent photos that we have, I think, news that we have seen. Last year we had a severe flood in Chennai, and just recently in September 2016, Hyderabad was flooded. Many areas of Hyderabad flooded with extreme rainfall in 2 days, continuously for 2 days on September 21st, 26th. But this is a common theme that you find in almost every city in India today. And there are different reasons. Many of them are man-made reasons because many times urban areas are not well planned. We don't have proper urban drainage system and encroachments of water bodies and all those things. But other reason that's attributed is there is an increase in the extreme rainfall in these areas. So what we observed in the recent past is that the extremes, both the floods and droughts are increasing because of the changing climate, and this becomes more common as we go further. So one of the reasons, several reasons are attributed for the intensification of extreme winds. Could be climate change, urbanization, deforestation, and others, many such reasons. But basically, in urban areas, urbanization and climate change are the major reasons which are attributed, which actually are the reasons why the extreme rainfall is changing. When we are trying to estimate the magnitude of an extreme event, when you are trying to design a water system. For example, in urban area, you are trying to design urban drainage system, urban stormwater drainage system. So we are interested in finding out, the magnitude of an rainfall event for certain frequency and some duration. So we use the concept of, for example, IDF curves to develop to find out the relation between the intensity, duration, and frequency. And this is something which very frequently is in hydrology. For example, I would like to know the magnitude of flood for a given frequency. I would like to know the magnitude of the rainfall event for a particular frequency and particular duration. That's what the IDF curves give. So what we are trying to do is we are trying to estimate the magnitude of the event for designing a system. And like for example, urban stormwater drainage system, or maybe an operational urban drainage system or flood control, in urban areas we use this concept of IDF curves. In fact, if you look at the scale at which you are trying to design a system, usually we have maybe at a particular location, I can always try to find out something what we call as estimated limiting value or largest value that is possible in the location for maybe, for example, rainfall or could be a flood. But usually when you are trying to design different systems, we use the concept of rim period. And for example, in minor structures we design of maybe a written rates of 500 to 1000 and more. So I think those who have studied hydrology, many of you undergraduate students, I think you will have studied hydrology where you do a frequency analysis. So what do you do in frequency analysis? You are trying to develop a relation between magnitude of the event and the frequency. So we use this for either doing the frequency analysis of extreme rainfall, for floods or droughts, and we can use the concept of written period. Like for example, I just showed the annual maximum flow at Polavaram. This is the annual maximum flow at Polavaram. And say if I am interested in 40,000, I think the line is not clear here. say, for example, I just take a magnitude of 40,000 meter cube per second. Now, we have 43 years of data here. Now, out of this, say this 40,000 is equal or exceeded, if you count this 10 number of times in the 43 years. So, this is where the basis of your concept of infinite, where you say that this 40,000 is exceeded approximately once in 4.3 years, because 10 times exceeded last 10, 40 years. So that's how we might say that the magnitude of this, or the return period of this event is 4.3 years. That means it occurs on an average once in every 4.3 years. Okay. So we can talk in terms of the probability of exceedance. So again, those who are familiar with the statistical modeling, you know that if I return period and the probability of exceedance are related, say the reciprocal of the return period is the probability of exceedance. So 1 by 4.3, that means probability that you are going to have a flood of 40,000 or more is 0.232. So this is what we are trying to estimate when I do say wave frequency analysis. We are trying to find the magnitude of an event for a corresponding probability of exceedance or return period, or for a particular magnitude, we would like to know what is its probability of exceedance or what is its return period. Now, how do we do this? We try to extract the extreme value data from a series of data that we have. For example, I just showed a Warangal data just now. Warangal is I think many of you know, Warangal is a gauging station on River Godavari, where a project is proposed now and is going to come up, and a lot of controversy surrounding it. But I have daily rainfall data, daily flow data for 43 years in that. Because we treat that as average flow per day. So we have for 43 years daily flow data at 4 hours site. That's what we call as a complete duration series. Now, but I'm not interested in the complete duration series. I'm interested only in the extreme value. In this case, I'm interested in the flux. So how do I get how do I extract this extreme data? One option is we'll pick up the maximum from every year, what we call as the annual maximum series. So we'll pick up one maximum from every year. What is the highest value in each year? So whatever extract the extreme value series. So it's what we call as annual maximum series. But one problem with this annual maximum series is when you're picking only one from every year, there is a possibility that you are missing certain amount of other extremes. The second largest value that you have in a next year could be higher than the largest in some other year. So this is one of the problems with the annual maximum series. So the other way in which you can extract data is to take what we call as partial duration series. You said you pick up a threshold value or some threshold value. Any value above that is considered as extreme. So pick up all such data. That becomes what you call as partial duration series. But the problem with the partial duration series is, as I'll show later, the entire concept of frequency analysis based on the assumption that the observations are independent. So when we consider the partial duration series, there could be the assumption of independence is not valid in case of partial duration series, because for example, say here you have taken 3 or 4 values, and there could be a dependence between these 3 or 4 extremes that you have picked up each here. The partial duration series, when you pick up a threshold and pick up all the values above the threshold value, the number of extremes that you get could be more than number of years that you have. But if you pick up the threshold in such a way that the number of experiences is equal to number of years of data we have, that becomes what you call as annual experiences. So we use one of these extraction methods in order to extract the extreme value data from that basic data that you have. For example, in this case, I'm showing, I'm taking the example of annual flow in a daily flow in a river. It could be daily rainfall or hourly rainfall. For example, I have hourly rainfall data of a city or at a particular gauging station. I'm interested in the extreme rainfall, extreme hourly rainfall. So I can again use the same process. I can pick up the maximum from every year, one maximum from every year, or pick a threshold and pick up all the values above the threshold, or maybe I can pick up the annual experience series and then proceed with the frequency analysis. Now, many of you are familiar with, I think you would have done frequency analysis in hydrology, those who are students here. So I'm just going to the fundamentals of this, what you call it, extreme value theory. So you have a series of observations x1, x2, x3, etc., which are all supposed to be independent observations, and another assumption that you're making is all these observations have a common distribution. Then you are interested in the distribution of the maximum of all these observations. So each observation, the probability, exceeds probability distribution, cumulative probability is the maximum I can say is because they're all independent, it's simply the product of this raised to power n. Now, if I apply the limit of any criterion, that's what we get is what is known as general extreme value theorem, which is a commonly used distribution for modeling the extreme values in a particular location. I think many of you are familiar with the second one here, the double distribution. It's a double exponential distribution, exponent of minus exponent of m minus alpha by beta, where m is the observed maximum, alpha and beta are the parameters of the model. A more generalized version of this double distribution is what we call as general extreme value distribution, which we say is which has three parameters. We have location parameter, the scale parameter, and this is called K is called the shape parameter. So when the shape parameter becomes equal to 0, that's what you get as Gumbel distribution, because all of us are familiar with Gumbel distribution. Maybe you were studying your hierarchy. We use Gumbel distribution for most of the time for practical analysis. So Gumbel distribution is a special case of what is known as general extreme value distribution, which has got three parameters. So this shape parameter becomes equal to 0. That's what we get is what is known as a Gumbel distribution. Now, once if I can fit a distribution to this data, for example, I have an extreme value data or what, say, for example, annual exceedances. So for this data, we fit a general extreme value distribution. If you can fit a general extreme value distribution, this what we mean by fitting a general extreme value distribution is if I assume that the annual maximum series follows a general extreme value distribution. From the data, we estimate the parameters alpha, beta, and k. Once we know the parameters, estimate the values of alpha, beta, and k. Now, you can use these values, estimated values of alpha, beta, and k, in order to estimate the magnitude of an event of return period q. So if the q is the return period, then the probability of non-X series is 1 minus 1 by q, and for that corresponding magnitude is there. So this is how we can try to make use of distribution in order to find the magnitude for a given distribution. I think, again, if you, those who are familiar with Gumbel distribution, you can recognize this expression. This is what we do in Gumbel distribution. You fit a Gumbel distribution for your annual exceedances. Find the parameters, the two parameters alpha and beta. Once you know that, the value of magnitude of the event with respect to q is given by this expression. Okay. So this is what we are basically trying to do in what we call as frequency analysis. Now, there are different methods of estimating parameters. Again, those who are familiar with statistical modeling, you have studied frequency analysis, maybe you use different methods. One is what we call as method of movements, maximum likelihood method, method of probability weighted movements, and so on. For example, this is Gumbel distribution. Now, I can set the movements of Gumbel distribution can derive from this expression. This is the probability density function, this is the cumulative function. We can derive mu is equal to beta plus 0.57 to alpha, sigma square is this. So if I can estimate the movements from the data, the mean and the variance, this mu is mean and the sigma square is variance. Once you estimate mu and mean square, I can substitute these values in this and estimate the values of beta and alpha. This is what we call as method of movements. But when you have small data, method of movement supposed to be biased, and that's the reason why it's not recommended. We go for, most of the time for general extreme value distribution, we go for what is known as maximum likelihood method, where we try to construct a maximum likelihood function. Once again, if I go for this Gumbel distribution, say, for example, this is the probability density function. I have a set of observations xi, let's say say some 30 observations, let's say. So I can consider likelihood function as a product of f of xi, means I substitute xi each observation into this expression and take the product, and that product is what you call as the likelihood function. So we try to estimate the parameters alpha and beta in such a way that likelihood function is maximized. That's what we refer as maximum likelihood method, and that's a way finding. Okay. Now, we have fitted a probability density function. Let's say this is a probability density function. Now, as you are familiar, the area of the probability density function will give you the probability of exceedance or non-exceedance. If I take the area on the left side, it gives the probability of non-exceedance. If I take the area on the right side of the curve, we get the probability of non-exceedance. I am interested in finding out a magnitude of an event with a little bit q. So what's the probability of non-exceedance of that 1 by q? That means I am interested in, say, this red shaded area is 1 by q, then the corresponding magnitude is what I am trying to find out. So for example, I have taken this as rainfall. So for example, I have a density function for rainfall, power density function. So ZQ is what you are trying to estimate. So if I say that means it is, you are trying to find out the value of ZQ which gives an area of 0.1 by q here. Or the other way, if I know ZQ, I can find the area that's more straightforward. I can find the area on this side, and 1 by that area will give me the return period of that particular unit. So, theoretically what you are trying to do here, you have a data, whatever, say either you are taking the annual exceedance series or the, the big O threshold data, and you are fitting a distribution to the data, a theoretical distribution, probability function. One possibility is you can pick the general XT value distribution. Once you know the distribution, then you are trying to find the magnitude of the event and find out, say, magnitude event for a given distribution period or for a given probability of exceedance. This is what basically what you are trying to do in what we call as frequency analysis. Whether it's done for floods or whether you are doing for rainfall, extreme rainfall. But the entire concept of this frequency analysis that you have been using is based on the assumption that your series is stationary. For example, I have a series here. What do you mean by stationarity? Now, I should say if I take local mean, that means, say, for example, moving average, something like a moving average, I take mean of some certain set of observations and then keep on shifting that window of observations. Then this is local, what we call as local average, and this actual series. So you find that the local average is almost constant. That means if your, say, any series is a set of random observations that you have, and this stochastic series, if the statistical characteristics of the stochastic series remain constant with time, we refer that as a stationary series. So in this case, I just showed with reference to mean, the mean is constant here. But I can extend this, I can talk about in terms of all the parameters to describe the statistical properties of this series. If they remain constant with time, then we refer that series as a stationary series. Okay. So when I talk in terms of the extreme value data, in the case of extreme value data, you are fitting a distribution to the extreme value data. That means you are assuming that the parameters of distribution are remain constant with time. They don't change. They don't change with time, so remain constant. So you based on the past observations, you pick the parameters and use these parameters to extend and then say predict what will be the magnitude of flight for maybe 20 years or 5 years or 10 years or whatever is the period. So that's a basic assumption that you are making when you are using this frequency as concept frequency, because you have a past observation. From the past observation, you are trying to fit a data to that past observations, and then so for example, I just showed non-stationary series. This is like it could be because of some seasonality or periodic component. So those who are familiar with time series modeling, you know how to model non-stationarity. But we are talking about modeling non-stationarity in an extreme value sequence. Okay. This is what I just explained the influence of non-stationary. So, for example, I have an observation, set of observations from the past, and then we find the statistical characteristics of this by fitting a distribution, and then use this distribution to find the magnitude of a particular frequency or particular return period. Now, what is the assumption that you are making that in the future also the same statistical characteristics will continue? But what actually is happening is your series is non-stationary. That means it cannot be remain constant with time. So it is changing with time. So in that case, your distribution itself would not be remaining constant with time. I'm sorry, the color combination. I think there could be a shift in your distribution. So that means your whatever estimate you are making from your past observation may not be valid or may not be true for the future, in the future, because your probability density function is still changing. So this is basically what we try to say. Maybe I think it's easier to explain here. Let's say this is the distribution that you have fitted based on the observed data, and then you found, for example, you are interested in a say 5 years return period event, and 5 years return period event, the probability of exceedance is 0.2, 1 by 5, 0.2. So this blue shaded area is 0.2. So correspondingly, let's say we have estimated that magnitude of the event as 90 millimeters. Okay. Now what's happening because of the change could happen because of this. I just said new climate, the climatic conditions and location may be changing. So your extreme rainfall could be still changing in that location. So there could be a shift in your probability density function. So when the probability density function is shifting like this, so the same 90 millimeters per hour, now what is probability of experience? It has increased. Now probability of experience of this 90 millimeters per hour has become this total area. Okay, so obviously this is more than 0.2. If it's more than 0.2, this one, say the return period is now lower. Let's say, for example, if this is 0.5, let's say this area has become 0.5. Now what's corresponding return period now? 1 by 0.5, 2 years. Means what you expect an event which is supposed to occur once in 5 years is likely to occur once in 2 years because of the shift in the. Anyway, I showed a shift like this. The shift could take place in the other side also. Okay, but what is happening is because of intensification, the shift obviously is expected this way. So how do you model this? Now we assume that these parameters alpha, beta, and k, they are not constant; they change with time, and try to express them as some function of time or as function of some physical parameter. For example, the change you can attribute, maybe you are attributing the change because of urbanization, or you may be attributing the change because of some other physical thing. So you can try to express this alpha as well as beta, okay, I showed alpha, as a linear or non-linear function of this, what we call as a covariate C. The covariate could be a time or maybe a temperature anomaly or urbanization, or maybe you assume that's because of ENSO cycle. So you try to attribute some physical parameter which is causing this shift, and then try to express your parameters in terms of that. So as the values of parameter changes, say values of this covariate changes, the parameters also change, and thus according to your distribution also is not remaining static with time, it is changing with time. That's the basic philosophy that we use behind what we say we model the non-stationary changes. I think I just try to just give a case study very quickly. A study that we have done in Hyderabad. In fact, you can see Hyderabad, how Hyderabad has gone from 1972 to 2013. This is again, okay, we took the land use, say we use the remote sensing data to extract the land use landfall pattern. This red area is the built-up area. So you can see from 1972, this was the built-up area in Hyderabad city. Now it has become like this. So the growth of Hyderabad has been exponential, especially in last 1 decade. Maybe in this time period, you find that suddenly there's a very steep increase in the area that's happening. This is how Hyderabad has grown. So obviously, it has got an influence on this. Obviously, any urban area, it's likely to increase the intensity of respiration because of what is known as heat island effect. Maybe you have heard about this heat island effect. In urban area, the heat gets trapped in the urban areas, and this heat can cause a change in the respiration pattern, especially compared to respiration. So it's the urban area, and so in this area, because of the urbanization, the heat gets trapped here, and when the wind flows in this direction, so because of heat island effect, this could cause a rise in there's a rise in temperature here when compared to the urban areas. So this wind, as it moves through this can change the circulation pattern in this area and cause an increased precipitation in the maybe downward side. That is what has been observed. This effect of heat island effect, change in circulation pattern, intensification of convective precipitation, and local variations, monsoon rainfall. We did some kind of studies based on, we observed that within the Hyderabad region, there's an increase in the rainfall when compared to surrounding areas. Rainfall area is increasing. We also observed that say we did a study on extreme rainfall in Hyderabad. We find that there's an intensification of extreme rainfall. So there's a, for example, I take 1 hour maximum rainfall. Say this is different rainfalls of different durations, and when we do a trend test, we find that except for this, most of these other durations, there is an increasing trend in the intensity of rainfall for different durations. So this we try to construct intensity duration frequency curves. Many of you may be familiar with what we call instantaneous duration frequency curves. A curve which gives relation between intensity of rainfall, duration, and the frequency with which the rainfall occurs. And we very frequently use this IDF curves, we commonly use this IDF curves for design of urban drainage systems and also small and estimating peak discharge from small catchments. So IDF curves are very commonly used across the world to actually, especially in urban areas and for small catchments. So we construct IDF curves for diversity based on past data. This is how typically IDF curves look like. So this is for each duration, say for example each written period, 2 years written period, this is the curve which shows the relation between intensity of rainfall and duration of rainfall. And we try to actually use the same methodology that I explained earlier to construct the non-stationary IDF curves, considering different covariates like these are the parameters which we assume that they affect the maximum rainfall in that. And this is how we construct the IDF curves. Now this is for say 2 years, 5 years, 10 years, and 25. Right now this is a 2 years written period. The green line indicates the intensity relationship that we assume stationary. If we assume non-stationary, the red line is for non-stationary model. Now if you look at the results, now if I consider 2 years written period, 1 hour duration rainfall, under stationary model we find that it's 42.85 millimeters per hour, whereas the non-stationary model gives an estimate of 53.86 millimeters per hour.
There's almost 11 millimeters
per hour increase in the intensity of rainfall.
11 millimeters per hour intensity and
Urban area is obviously a very quite a
significant value.
And another factor that we observe is
If I consider 5 years written period or 1 hour duration, the stationary model has given 2.26, which is almost equivalent to, or in fact smaller than the 2 years written period event of non-stationary. So if we are, say for example, if you have designed a urban drainage system in Hyderabad city for 5 years written period rainfall, so and we design for 2.26, what we
observe now is because of this non-stationary, because of the urbanization and intensification of rainfall,
this event could occur once in 2 years, not in once in
5 years. So the system could rain more frequently than what we anticipate. So this is how the intensity duration, we can try to model the intensification of rainfall in an urban area using what we call as non-stationary modeling. In fact, we can also apply the climate change model, but let me summarize this. This is what we actually observed.
Try to actually correlate why this
intensification of rainfall is taking place in the city of Hyderabad. We observed that in the case of short duration rainfall, when I consider 1 hour or 2 hours of the short duration rainfall, in fact the local climate is or local causes like for example local temperature anomaly and urbanization, these have more influence on the change taking place there. Whereas in the case of long duration rainfall, we observed that these parameters, the global parameters like IOD and EMF cycle, these global temperature anomaly, they are more influencing on the change, the non-stationary or change in the intensification of rainfall.
Skip this part. We also try to construct IDF curves using climate change
modeling. Wait, time shortage. I'll skip this part. Thank you.